My thing just stopped recording, so I'm just gonna make a part 2 video, I guess, just leaving off where we picked up. So, if we have, right, I was in the middle of writing this equation, right? The inertia of the shape is just equal to the inertias, right? These point masses, this is like our point mass equation. It's actually given to you. If you check, it'll say that the point mass, the inertia for each point is just mr squared. You can just add them all up. If you're clever, you can say that, hey, I shape, the distances are all the same. In this scenario, where 0.7 is the distance for all of them, I can just factor out an r squared, just some math here, and then you can just add up the masses. So you can do m1, so m1 plus m1, there's two m1s, right? Two of the lighter ones, plus two m2, two of the heavy ones. If you just want to like plug in each number here, that's totally cool too. The math, some people just like simplifying. Makes it easier, right? Because when you're calculating, you don't have to type in a bunch. But it's really just 0.7 squared plus, and then, 2m1, which is 2, m1 is 3, plus 2 times m2, which is 5. Because they have different masses. You should get, I don't know if I did it right, because I got 16 point, I don't know if you can see that, 16.49. I wrote down 7.81, so I don't know where I made a mistake. Let me just check. Because I did 0.7 as radius, square it, and then I did 2 times 3 plus 2 times 5. Should just... Oh, because I forgot to multiply. Okay, let me try that again. I think you should get something like 7.8. Yeah, 7.84. So there you go. Pretty simple there. So I shape is going to be, what was it? 7.84 kilograms meters squared. And then we gotta calculate the rotational inertia for the horizontal thing. The horizontal, sorry, I was reading the problem again. The horizontal center, or axis of rotation. So if you imagine this was our axis of rotation, you would imagine it would sort of, if this was our thing, it would rotate like that, sort of towards you. So now, it's really the same idea. This time, when we're calculating the rotational inertia, these two masses don't add rotational inertia because they're right on this axis of rotation. Mathematically, that would be like saying, okay, this mass, r is 0, right? It is 0 distance away from the center axis of rotation. This r is just 0. Same for the other m1. So now you just have m2 r squared plus m2 r squared. You can easily just do that in your calculator. Hopefully, if you made it this far in physics, I think you can. So 0.7 squared times 5, and then multiply by 2. You should get 4.9-ish. I think. I hope. Oh, no, you shouldn't, because it should more be 0.7 squared times 3. Yeah, you should get 2.94. So what I did is I just took I don't know if you can see, I just took the distance, squared it, and then I just, multiplied it by 2 again, because I just did this times 2 because it's 2. You should get 2.94. Hopefully this is making sense so far. I know when I learned this, it wasn't 100% clear to me why. This is like why rotational inertia increases with distance. I'll maybe make a video on that, like explaining why. But for right now, hopefully this is making sense to you. So I'm gonna do page 46. I'm gonna verbally do a lot of these just because, I don't think you guys need me to write out everything. I'll do the graphing ones too though. So I'll just actually take the binder. Suppose you do another test with this with the windmill setup, right? And you put the mass at the very end of the windmill blades, you record the time, and then you get much bigger masses and then add them to the end of the windmill blades, right? So if we think about what that's going to do, right? If we have our little thing, you measure the time to take for the mass to fall. I don't know why I drew it like that. But then you add more mass. You can imagine that's increasing the rotational inertia. It's the same, in theory, the same torque, but because the tension is still the same, but now there's more rotational inertia, now you're gonna get slower or less angular acceleration, right? And this kind of goes in with our second question. What is Newton's second law for rotation? It's just torque net equals inertia, rotational inertia times angular acceleration. This isn't something completely, earth-shattering. This is literally just F net equals mass times A. I don't know if we talked about this in class, but mass here is our inertial mass. That's actually what scientists call it, inertial mass, because it's saying, okay, for this much F net, for this much inertial mass, if you have less inertia, you get more acceleration. Same idea applies here. Sorry if what I just said was really confusing. I know inertial mass we don't really talk about, but inertia is mass. That's really what it is. So inertial mass, inertia is mass, whatever. Question 7. In your own words, if something has large rotational inertia, what does this mean? Just means it's harder to angularly accelerate, right? If you have more rotational inertia, you need more torque to get the same acceleration, angular acceleration. In your lab, your group graphed torque versus angular acceleration. Okay, yeah, this question was kind of confusing. What it's asking though, real quick, it's just saying that, hey, if you had torque net versus acceleration or angular acceleration, and then you had angular acceleration here versus torque net, right? You graphed it. Let's just talk about the slopes and stuff. You have torque net and then angular acceleration. So you can see if you have zero acceleration, angular acceleration, that means zero torque is applied. If you have a lot of angular acceleration, a lot of torque is applied. So the slope here is just inertia or rotational inertia, because torque net over angular acceleration, right? So if you say torque net equals rotational inertia times acceleration, right? Divide everything by acceleration, you get inertia. And I'm dividing torque net by acceleration because that's just how you find the slope, right? Your change in y over your change in x. Y, x. So that's the slope. The units of the slope is going to end up being kilogram meters squared. In this case, it's very similar, but this slope is saying, okay, for a certain torque, I get this much acceleration. This graph is saying if an object has this much acceleration, it has this much torque being applied. So same thing here, if I do angular acceleration over torque, that's going to give us 1 over our rotational inertia. And once again, this is literally just coming from if I divide this side by torque net, right? Then I get, 1 is equal to inertia, acceleration over torque net. Divide everything by inertia, right? You just get 1 over inertia, rotational inertia. Every time I say inertia, just assume I mean rotational inertia. 1 over rotational inertia just equals alpha over t net. Little math to just prove it, but the whole conceptual idea is just like the slope, right? And then the units is going to be 1 over kilogram meters squared. Yeah, there you go. That's actually all you need. But yeah. So if you had, I'm just going to show this one. So if I just take my packet, if you had, where is it? Yeah, a graph like this, group B has a less slope, or group A has a bigger slope, right? Torque net versus acceleration, we just talked about. Torque net over acceleration, the slope is rotational inertia. This is different from what we did. We did this. We did acceleration versus torque. That gave us a different slope. In this case, right, if you're doing torque versus angular acceleration, more slope means more rotational inertia. Let me kind of show you. For this much acceleration, this group needed that much torque. This group needed more torque. So the greater the slope, the more inertia, right? The more torque you need to get the same angular acceleration. Question 11, final question here. If we were doing angular acceleration versus torque, right? And we kind of talked about this in class, if you're in Mr. Fitt's class. If one group used the pulley, because we had like 3 different pulleys, if you use the outer pulley versus the inner pulley, right, and everything is still like the same setup. You still have the same masses and stuff, and the same distances. We're just changing where we put the mass, in the inner pulley or the outer pulley. The outer pulley, radius is bigger from the axis of rotation. That means more torque, right? Because same force, more torque. And then when you do it in the inner pulley, less radius, less torque. However, what you're actually going to find is it's going to still be the same graph. And we talked about this, right? Because we said, okay, if you apply a greater radius, that means greater torque. So you're going to get values up here, right? Because if you apply a greater torque, you just get more acceleration. If you do it in the inner loop, you have less torque, but you get less acceleration. Everything falls in the same slope. But now, this makes a lot more sense because what stayed the same? The rotational inertia stayed the same, right? The masses had the same distances and everything. So now, what that means is, right, the slope is 1 over rotational inertia. So if you had the same rotational inertia, so 1 over rotational inertia is the same, the slope is the same throughout the entire time. Doesn't matter if you do higher radius, higher torque, or if you do lower torque, you're gonna have the same slope. So I hope now that makes sense, that if you have the same rotational inertia, higher torque still means higher angular acceleration. The slope is going to be the same. So yeah, that was worksheet 9, part 2. Sorry for cutting off. Actually, I think it's a good thing because now this is like 12 minutes. Yeah, so thank you for watching.